Modern factory floor realities are currently stripping away the sci-fi dream, replacing bipedal humanoid aesthetics with utilitarian wheeled platforms. In May 2026, Goldman Sachs deployed a research team across Shenzhen, Beijing, and Hong Kong to audit 14 of China's leading robotics firms. Their mid-year report delivered a clear conclusion. Embodied AI is rapidly approaching commercial reality, but achieving actual scale means abandoning the bipedal, human-like form factor. The industry is pivoting. Manufacturers are actively shedding complex designs to survive the brutal unit economics of real-world deployment. Stripping down the hardware solves three critical bottlenecks simultaneously. It slashes the bill of materials cost, accelerates physical data collection, and simplifies the integration of the robot's cognitive architecture. To see exactly how this works, we are going to reverse engineer the 2026 pragmatic robotic blueprint, layer by layer. Engineering a mathematically viable path to scale requires prioritizing unit economics over human aesthetics to fund the development of true robotic intelligence. Getting a robot onto an industrial floor requires surviving a grueling three-stage pipeline. It begins with months of proof-of-concept testing, moves to small-batch pilots, and only hits large-scale deployment after a year of continuous validation. Surviving that cycle dictates strict engineering discipline. Form must follow function, leaving zero margin for vanity engineering. Right now, a wheeled chassis equipped with basic 2- or 3-fingered grippers can execute 90% of immediate industrial applications. Intricate 5-fingered hands lack the durability for industrial loads, suffer frequent mechanical failures, and impose excessive costs on the manufacturer. Consequently, leading firms have paused development on intricate hands, opting instead for ruggedized, high-reliability grippers. The simplification of the hand is just one symptom of a larger physical constraint, the bill of materials. This chart maps hardware cost reduction, starting at a baseline of 400,000 RMB. Swapping CNC machining for injection molding drove costs down to 200,000. By pushing volume higher, the industry targets 100,000 by 2027. Rows of identical wheeled bases advance uniformly through an automated assembly line, providing the scale required for mass industrial deployment. Aggressive hardware cost reduction provides the capital to finance intensive software and data infrastructure. The physical robot has been downgraded from a luxury showpiece to a disposable, cheap vessel designed solely to carry a highly valuable digital brain. That digital brain is starved for input. Industry consensus dictates that massive commercial deployment is constrained entirely by data, requiring tens of millions of hours of physical telemetry to solve. Manufacturing thousands of hardware units is useless if you lack a scalable operational policy to actually drive them. Developers organize training data into a 5-tier pyramid architecture. The bottom 2 layers provide foundational knowledge via scraped internet data and physics simulators. The top 3 tiers contain high-fidelity, human-in-the-loop teleoperation data, mapping human physical decisions to the machine. Acquiring this peak-layer telemetry is resource-intensive, triggering a race between 2 distinct collection paradigms. This map illustrates the first approach, centralized data factories. These are regional hubs, often backed by local governments, built specifically to mass-produce physical motion data. These factory pipelines are so critical that they accounted for roughly half of total enterprise demand for robotics hardware in 2025. The second paradigm skips the factory floor entirely, utilizing distributed wearable telemetry networks. A haptic suit wearer moves their arms in a domestic setting, instantly digitizing precise motion data for a wireframe model. Companies are deploying a rental model where telecom operators lease these suits to everyday users, allowing them to capture telemetry at home and feed the dataset. Developing embodied AI at scale has evolved into a massive physical logistics operation, requiring immense capital for data acquisition. How do you mathematically process millions of hours of physical telemetry into autonomous action? Leading firms are standardizing their software stack to handle this, relying on a dual-engine architecture that runs vision language action models, or VLA, in tandem with world models. This diagram of the fast WAM model demonstrates this split architecture. The upper path is the world model. It takes visual inputs to continuously predict the next physical state. The lower path is the VLA policy engine, generating mechanical action chunks to achieve that predicted state. Some architectures are evolving even further into VTLA, integrating tactile force feedback data from physical interactions to refine their mechanical grip. Running this dual-engine approach requires immense compute power, with model sizes scaling from 1 billion up to 80 billion parameters. Compressing these massive parameter stacks into a physical machine requires rigorous multi-round iteration to reach true stability on a factory floor. A modern robot's intelligence relies on this constant loop, a dual-engine architecture continuously predicting the future while simultaneously executing the present. Currently, these operational environments remain narrow and highly structured. The commercial beachheads are specific, repetitive workflows, such as material sorting or inspecting battery cells for leaks. The timeline from the Goldman Sachs report maps out exactly when this expands into true, massive commercial deployment. Pushing past the pilot testing of 2026 into the standardized product scale of 2028 requires a methodical, uncompromising grind. Dozens of wheeled robots maneuver with silent, repetitive precision through warehouse aisles, executing complex sorting tasks in perfect algorithmic unison. To afford the vast compute needed to build a complex, world-simulating digital brain, developers had to first compromise on building a simple, cheap, and strictly pragmatic physical body. The embodied AI revolution is deploying today as a silent fleet of hyper-optimized, data-hungry machines, rather than a parade of androids.